There. Okay. So what we want to talk about was deep learning and specifically unsupervised learning. And so I put together a little presentation, little demo app. I go through some of it. I'm not happy exactly where it's at. And I'll talk about why, but I think it's a good first start. And then the better one will be when we actually get to back to the science center and can meet in person and see it on the actual robot running around doing things. But what I wrote for this was an unsupervised learning algorithm to learn to play tic-tac-toe. No, why is that not? Hold on, sorry. Find out. There we go. Okay, is to play a tic-tac-toe game. I wrote it in C#. Because a couple of reasons. One is it's a little easier to follow the logic of the app in C# than it is in C or C++ or another language. Neural net training also isn't generally suited for microcontrollers because of the memory requirements and the speed, the time it takes to process that. And C#'s reasonably fast, and so gets through it pretty quick. The robot, and generally for neural net training, you're going to train the model offline somewhere on your laptop, more powerful computer, get the built model moved to your robot, and then let it execute. And executing a neural net is extremely fast. Still requires a lot of memory, but that's why I did it in C#. When we use the term deep learning, that's very synonymous with neural networks. There's a lot of different versions of deep learning and neural networks, and the one we're going to talk about today is called backpropagation. And in backpropagation, we first train the model and then use that trained model to play the tic-tac-toe game. So what is a neural net? It was developed in the 1970s, kind of languished for a long time until about 1987, where there was a paper written demonstrating the power of it and what it could do and blah, blah, blah. So it kind of took off then as one of the first AI algorithms that now AI is now generally called analytic, big data analytics and things. But the thought was in the 70s, like, well, if we're trying to make artificial intelligence, how can we model the way a human brain works or any animal's brain works? And so they built this idea of neurons that are interconnected that fire based on stimulus. And that's how they built the algorithm in the computers. So if you look at this model of a human neuron here, there's dendrites that take stimulus inputs, combine those stimuli into an output signal that then gets propagated down to more neurons that'll fire based on how strong each of those signals are from the axons and the dendrites. That's basically how a neural net is modeled to work too. Neural nets are generally best at clustering and classification problems. They can be used in other things. As it turns out, a neural net's not really great at playing tic-tac-toe, as I found out. But it's we're still gonna. It doesn't make an expert tic-tac-toe player, but it does show the idea of what we're trying to get at. So a neural network in code is this is going to be hopefully the only your eyes glaze over slide that I've got. But this is the math behind it. And so what you build up with a neural net, just like you saw in those biological neurons that it tries to model, is interconnected neurons called perceptrons that have weights and a mathematical model that governs the firing between the neurons. And so what you generally do is you've got, this is why you can't really point very well. Yeah, it does. Okay. So on the right here, you see you've got an input layer, which are obviously your inputs, and then an output layer, which represent the signals coming out, your classifications, and then one or more, well, technically zero or more hidden layers in between. The hidden layers give you nonlinearity in the response. So, and we'll talk about those extra layers in just a little bit, but basically those hidden layers are there to let you model things that are um, high orders of, like to the third order, fourth order, fifth order kind of cycles in the data. So very noisy, very erratic data can be modeled very well. And that's probably the real strength of this. So for a typical application, you would have, or in robotics, you see a lot of this being used with the input layer being a video image. And so you would have an input layer where there's a node per pixel on the image you're processing, and then some numbers of hidden layers. And then finally, the output layer would be one node per classification, right? And I think we saw somebody brought in, or we did a demo months and months ago now, using what's it called? Oh, sorry, I'm blanking on the name. The TensorFlow. I think we used somebody had used TensorFlow. TensorFlow uses these neural nets, but it's most of their algorithms are very visual based. So you give it the image, it breaks the image up into pixels and regions that are put in the input layer, and then the output layer you train to say, oh, this is a dog, or this is a steering wheel, or this is a doorway, and it can classify those and extend those then to very noisy data. So that's sort of what this whole structure is about. The way the algorithm works is you go from the input node, and then each node of the input layer has a connection, a pointer, a reference to a node in the next layer down, so into the hidden layer, for instance. Each of those connections is given a weight, and that weight goes between, in most cases, between -1 and 1, where -1 means very much that's not an association, and 1 means very much it is an association that ought to be built. In the middle, those areas that are kind of transitional, fuzzy areas, if you leave that very binary, a stair-step function, the neural network tends to be very erratic. It'll because it's all like no, then all of a sudden it hits a value where, oh, yep, that's it. There's no in between. And so most implementations use an activation function called a sigmoid function. And that's down here on the left, the lower left, where the output is very binary except in that transition region. And it's called a sigmoid because it looks like an S. It as you sum these things up, you go to the first node, the first input layer node, and you add up the weights. The weights of each of those. Well, you go to the first hidden layer node, and you add up the weights of each hidden input layer node that's feeding it, and then you add a bias onto it, and the bias is there to kind of just keep it from ever being zero, because if these things start to zero out, you'll just have no result. So you need to be sure you've got a bias in there. You add all those up for the first hidden layer node, add up all of the weights from the input layer, and then you run it through this sigmoid function, and that gives you a value, and that's the firing value of that hidden node. Then you go to the next hidden layer node, and the next and next and next, and do all those things. Then you move on to the output layer node, and you do the same thing again. And the idea is that when you add all these up, the input layer nodes that end up not really having an effect end up being kind of zeroed out or made very, very small. And the ones that really contribute to your decision become very strong because you're adding them all up across the system. That's sort of how it works. I'm not going to go in. Is there any questions about that or anything that people want to ask? I don't want to go into too much of it because it gets really, you can spend hours just talking about that. But that's generally how this is going to operate.
One thing I keep reading when I read about neural stuff, they talk about introducing some randomness initially. I think is that the bias layer or part of it?
No, the bias layer is actually something you kind of build in ahead of time because if you want to force certain nodes to fire more strongly, it's a tuning technique. What you're referring to is these weights I talked about, right? Training the neural network is calculating the correct value for those weights. And since if all the weights are 0 when you start out, you get everything adds up and it'll just always be 0 because of it's a multiplication, right? Or just be the bias. And so what you do to start with before you train the network is you set all the weights to a random number, some small random number between generally -1 and 1, just to give it somewhere to start that's not all 0. And in training, I didn't talk about training, but what the training does is it's called, we're going to talk about one called backpropagation, where you set the output layer and you say, for this output, let me go back and propagate that backwards through the input and see what the input should be for that. And it's obviously wrong. So then you adjust the weights in a way called steepest descent. So you find how to adjust each of the weights in a way that makes the solution a little better. And then you give it another example in the output and say, this is what the output should be for these inputs. Does it match up? Nope, there's an error. Readjust them again. And you keep doing that over and over with every element of your training set until the errors become low enough that you kind of don't care. It gets down to the point where it's a good number. That randomization is about setting those initial weights when you're training so they aren't just 0.
All right, thank you.
Make sense? Anything else? All right, we'll get off the eye glazes over stuff. So what is this really? This is really just fuzzy nonlinear regression is all a neural net is. And so what you're doing here is I made a graph of input values and output values. So you can think of this as the input values are all the pixels of an image, and the output value is the classification of the person that it recognizes or the object that it recognizes. And so you start out with a bunch of different, each of these little triangles are your training data sets. As you train it, what you're really doing is setting the weights so that for a given input, it comes up to the red line and says, oh, well, that's obviously the output for that, right? And so that's why it's very useful as a classification algorithm, because it narrows the dimension, called narrowing the dimensionality of the space. You take 1,000,000 pixels off a screen, 1,000,000 dimensions off the screen, and you narrow that down to 10 or 12 images, 10 or 12 classifications that image is. Now, it can be 2 hidden layers. We talked about the hidden layers before. If you do 2 hidden layers, you can model up to a 4th order polynomial with that. So something to the power of 4 in curvature, right? So there's a lot of, with just a few hidden layers, you can really make a lot of very complicated curves out of this. It can be fooled, and it's kind of easy to fool this. Let's say, for instance, you had input data that was had different input data had different results, right? That some of the input data showed this output, but similar input data could show a different output. The model is still going to split the difference. It's going to come draw that red line up through the middle of those two very different data sets and go to make bad data. So when it gets beyond this first cluster, it's going to start making bad decisions. No matter how much you're not going to out train it for that. You're not going to make it better. It's just going to be bad. What this type of data set shows is there's really 3 neural nets you need to make. You need to make a neural net for each of the 3 clusters of data. So they can be good, they can be bad, they can, depending upon the data and what they're trying to classify, and how much of that they've seen in training, they can give good results or horrible results. So understanding the data and solving the problems aren't always just a matter of, well, just train it more, right? Sometimes it just isn't going to get there from here. We talked about backprop a little bit already. It's about understanding how the changes in weights and biases in the network change that cost function. So you build a cost function that says this is how much error there is given an input and an output that I've got in my training data, and then I evaluate that expression from output to input. We talked a little bit. I just already talked a little bit about that, but go backwards, and then you look at the gradient, which is the steepness of the curve. You understand the error. You look to see how you move that weight so that you take the most error out of that example. And that's where the backwards propagation of the error comes from, why they call it backprop. Okay, enough of that. Let's talk about code here. Let me get that up. Any questions before I go actually into some code? All right. That. Let's flip forward here to get at that. Okay.
Quick question.
Yeah.
Thus far, is the robot that you're trying to teach tic-tac-toe, is it your computer or is it something else?
This is my laptop right now. I'm trying to. I would put this on a Raspberry Pi. You can run this. This is in C#, so you can run it on a Raspberry Pi. If you bring down Mono, you can train it on your laptop, and then move the trained model. Once you get the model where it works well, just move that model off to your robot, which is really what I would suggest. The training is the computationally intensive piece. It's also the most interesting piece. Once you have the model done, it just kind of executes. What we're going to do here is called unsupervised learning, and so I don't have a specific training set for it. I'm going to have it play tic-tac-toe for some number of games and see when it win, what winning combinations are and what losing combinations are. It's going to look at those games and try to figure out moves that lead it to win more often. It's not an exact algorithm. It's not a, there are game models where it plays the whole game out and finds specifically ways it can win or lose. That's not this. It's going to play a bunch of games and bias moves its next move based on what in the past has worked well for it or not. And so that's why in this case it's unsupervised. Its goal is to win. If it can't win, it wants to tie because it doesn't want the human player to win at all. And so that's what it tries to do.
All right, thank you.
Okay. Did everybody see the code all right? Is it big enough on the screen?
It's a little.
Could be a little bigger if you can.
All right, let me get that. Yeah, let me get that. Get this out of the way. Move my monitor and unplug something. Is that better?
Yeah.
I can move some of these things out of the way too. All right. And then don't need that. That'll help. Okay. So this is main. There's a variable up here at the top just called the number of training games. Got it set to 1 right now. And then the first thing it's going to do is I'm going to call this method that I wrote called train the model, and I'm going to tell it how many training games to run. That's going to return to me then a model that has been trained. What you would do normally would be, or in a robot, I think, would be take this model, this class, write it off to a file so you can save it, move that file over to your robot, and then upload it into the algorithm that's going to run your robot. And so that's sort of the 2 steps here. This top step is training the model, and then the code that's under here is really just playing the game based on that model to show you how it works. But this model class, you can take that data, write it to a file, and move it, and then you would upload that, and then your robot would do the rest of this stuff. So by convention, player X is always the first player. So I've got a Boolean value to keep track of whose turn it is. We start with X, and we go into a loop, and we make a tic-tac-toe game, which really is just the rules of tic-tac-toe. And then we iterate through, we go to another loop where we're playing until the results, or playing while the results are still unknown, while there's no winner, no loser, no tie. Print the board out, and then if it's X's turn and the human is player X, then you ask the user to choose a square. And if it's not, you ask the game to make a move based on the best square the model picks out. So the model looks at the current state of the board, which is game, the current state of the game, does its inputs and outputs, run. So the inputs in this case to the neural net is the state of the board. In the 9 squares of the board, where is there an X and where is there an O and where is there an empty space is the input to the neural net. It runs through those calculations and it says, of the 9 output spaces that I have potentially left, or however many I've got left, where should I put my marker is the output. That makes sense? And then it tells the game, well, make that move there. Okay. And then once you finally get a result, you put that result out. Oh, somebody won or somebody didn't. If nobody's won yet, it goes back up to the top. This time it'll be the other player's turn. The human chooses, and then once the human chooses, then the robot chooses again and picks the new best square. That's how it goes back and forth. Okay. So the play of the game is actually very simple. Let's take a look really quick at this best square algorithm, or the best square code. So that's right here. It sets the best score to negative infinity, so that it's way out of range. There's nothing worse than that. And then the best square, it just says is 0. Just start somewhere, and then it goes through for each square in the valid square. So an invalid square would be one that already has a move in it. So it looks here, and for each empty square, it looks, it gets the game board So the neural net needs doubles as its input, and so it converts the board into a double array based on who the move is. So 1 is always the player, -1 is always the not player. And so depending upon how this is, who it's evaluating for, it has to evaluate whether the player's in a good spot or the computer's in a good spot. So that's why it kind of has to do that, tell it whose turn it is. But it builds this double array, and then it computes the score. If the computer were to place its X or its O in that space, what's the value, what's the score of that move? And if the score is better than that score, it keeps track of it. And it goes back and finds the next one. Oh, is this move better? And it keeps going through all the empty squares until it finds what it thinks the best move is. And then it just returns, this is the best one I think to play in, right? And so that's all there is to the model. So that's what this is doing. So this is just going through each square turn by turn, figuring out where the best, it thinks the best move is, and then telling the game, move me there, right? Let's look now at the training, at the train the model class method here. All right, that's here. We make a class called trainer. We'll go look at that in a second. That's where all the real intelligent work gets done. There's some timing stuff up here just to show it starting, because it can take a minute to train this. The real interesting work is done here with telling the trainer to train on this number of training games. Everybody okay so far? All right, let's go take a look at the trainer. So the trainer is where things get interesting. There it is. So I'm using a library here called what's called. We'll look it up again. I forgot the name of it. Something aforge.net is the it's a C# library, C# neural net library. That's much like TensorFlow, but it's written in C#, so it's easy to call from C#. You could move this over to TensorFlow or TensorFlow Lite just as easily by changing the names of some things. But one of the things that's in aforge, their activation network is what they call their neural net model. And so we're going to build that neural net. We're going to tell them I want a bipolar sigmoid function as my transfer function. That's what we talked about earlier. Bipolar means it goes from -1 to 1, not 0 to 1. There's a lot of these you can try. This one's kind of common. Other ones may give us better results. I haven't had a chance to really look at everything. I want this first value of 9 is the number of elements in the input layer. And let me get the rest of these. Where did I put them? Find the rest of them. I got to look up the rest of the parameters. There it is. Okay. Yeah. So you pass in the activation function as the first parameter, the number of input of nodes in the input layer, and then the number of neurons in each of the other layers you want. So in this case, we wanted 3 layers. So we put the first 9 as the input, and then the hidden layer is another 9, and the output layer is another 9. Right, so we've got, well, yeah. So I'm sorry, no, we got 9. There's 18 more neurons. There's 9. How does that work? I lost track of that one. It is the number of neurons in each layer of the neural network. And so the count, network's input count, yeah. So nine inputs, and then I got, this has multiple layers. It has 18 layers, 18 nodes in the second layer, 9 nodes in the third layer, 3 nodes in the fourth hidden layer, and then finally just 1 node coming out to say what the value, what is the score of this move. So this has 1, 2, 3. This has 5 layers. Doesn't just have 3. It's got an input of 9, and then there's 18 layers. So each of these first 9 squares hook to 2 each. And the logic behind that is there's either a weight you want to go and say this is a good X move or this is a good O move. And so 2 times that gives you that binarization really early in the execution, right? So it's going to say this is going to be an X move or an O move, and then you start cutting it down, get it back down to 9, and then reduce it a little more to 3, and then finally your 1, which is your score. Setting these internal nodes up is kind of just trial and error, black magic experience. It doesn't. There's not a set way to do it, and playing with them, you're trading off memory versus and performance. Performance is going to go down with more nodes. Memory consumption is going to go up with more nodes, but you can model more complex functions also. And so that's what you kind of, there's just no way to do that except experiment and try, see what works better or worse.
Can I ask a question?
Yeah.
So I guess the way I've seen it done in the past, looks like you're evaluating each move individually. I guess the way I've seen it done, not necessarily tic-tac-toe, but you'd have 9 outputs and you'd have 9 inputs. So because your 9 inputs would be 1 for each square, and then your 9 outputs would be all the possible squares that would want to move to. And they would weight each of the outputs, and then you choose the highest output to choose the move.
Mm-hmm.
But you're doing it differently here than I've seen. Is that because of the reinforcement learning, or?
It's because of it makes a more crisp output. If you've got 2 that are kind of close together, they're gonna kind of fight for dominance in the algorithm. I don't know how to explain that exactly, but it's neural nets as classifiers want to come up with an answer, not a bunch of answers. Now, if you were looking for degrees of membership, so here's a good example. So like the example where there's an input image and a lot of different possible outputs you might have, then I would use that kind of model because you're looking for a degree of membership, right? I got my image here. What's the degree of membership of a car or a chair or a window or a door or a person, right? Maybe those are the outputs that I'm going to classify. I want to know how much of it is to each one, because sometimes 2 of those close together mean something to me, right? Well, it's kind of a car or a model car or a big car. Well, maybe now I want to run the algorithm again and have it choose something else on that reduced set. Where for this game, the choice comes down to a single binary choice, which is, do I put my square, my X or O in this square or not? Does that make sense?
Yeah. Which input would be the square you're selecting to? So you got 9 inputs. I assume those are the
That's
position.
the state of the board, right? The 9 input layers are the state of the board, right? Which is either empty or filled, right? It's either an X, an O, or an empty is the 3 values. So those first 9 input layers will have a 1 in it if it's your square already. It'll have a -1 in it if it is the opponent's square already, and it'll have a 0.01 in it, because you don't want it to really be 0, a 0.01 in it if it's an empty square. So that's what the inputs are going to look like.
Okay, I think I understand what I was missing. So there's the input's included in the board array. So you're giving a different board, a future possible board, and it's evaluating how good that outcome is.
Right. So when I build that board, as I go through that loop I showed you a minute ago, where you go through and look at each individual square. If it's a valid move, meaning if it's empty, well, what happens if I put mine in there, and it'll evaluate that. And does that give me the best curve fit for a winning solution? So that 9 element array will have, like I said, a 0 in it, or a 0.01 in it if it's empty, a 1 if it's mine, because that, as that goes into that activation function, that's going to positively build the output number. Remember, because I'm taking all these inputs and I'm going to the next layer and I'm adding up all the inputs. Well, if I've got 3 in a row, or if I've got connections that make me a stronger place, I want those to add up. But if my opponent is on those squares, that sort of takes away from where I want to move. And this may not be the best algorithm to solve tic-tac-toe. And when we started playing the game, I can show you that it still makes some stupid moves. It gets better as it gets trained, but it'll still make some poor moves as it goes on. So there may be some playing to do here with some of this stuff to make it better. Is that anything else?
No, yeah, I'm clear on it now. Thanks.
Okay. So then we create the next line down there on line 25. We create the backpropagation learning, which is the thing that actually does the training. This backprop algorithm is in that second piece. So the first piece is the network that we're going to end up with. The second line 25, is the backprop algorithm. And then this was a question earlier, you randomize, right? What's the randomization? So net is the neural net, right? Which is all the weights, all the summations, and you randomize those to not have it be all 0, not have it be, it all makes reasonable numbers. And then you set a learning rate, which is very common in AI applications. In these algorithms where you're trying to set a bunch of different variables that all interact, if you made that 1 or 10 or some big number, what you end up with is oscillations in the data. You can't ever stabilize onto data. Think about PID controllers and the gains on PID controllers. If you set the gains too high, you end up with oscillations, right? Because you're always way over correcting. So you make the gain smaller so that the first time through, the correction is 75% of the total error correction, right? And then the next time is 75% of what's left and 75% of what's left, until you get down close. If you set the gain too high, you overshoot, have to come back and you overshoot, right? Everybody get that? This is the same thing for these learning algorithms. This learning rate, it's called alpha, is the common term for it in most of the algorithms, is a way to dampen those oscillations of the learning, so you don't overshoot and get into situations where you never do get to good numbers, because when I change this weight and it gets summed into the next one, it creates a huge error, which then affects a bunch of other numbers, and everything moves back and forth and you never get there. So the learning rate slows down learning so that you can edge in on the right number slowly without oscillating. All right. The next loop here is you go through from 0 for the number of games you want to simulate. How many learning sets do you want to look at? and you build a training game, right? And so, or you go play a game. So you pass in the neural net, you pass in the players and some stuff, um, and then we'll go down and look at that and decide how you actually play that game is the second. But you end up getting the inputs and the outputs off of the training game, and then you run the teacher, you run the backprop algorithm showing for each input and each output of the game, each move of the game, did it make you better or worse? And so you're doing this backprop every time. And then you go back and you do another game, and you do another game, you do another game. The idea here is that in this case, you're kind of generating your trading data based on just playing the game. You could change this loop, and I thought about doing this. It made it very difficult to explain what was going on because it integrated the gameplay with the algorithm. So I didn't do it in this example. And it ends up turning out that you need to play so many games to get this thing to learn how to play that it was impractical. But what you could do is have this be live so that you have it play a game, get its butt kicked, but then it learns from that and improves, right? And you go back. So instead of having this play a training game, you have that be play a real game against the user and then go improve its model and then go back and play another game against the user, improve its model, go back and play another game against the user and play its model. And that's how humans really learn, right? We babies were on the laying on our backs and kicking our arms and legs, and we don't do anything. Eventually we learn to reach out and touch something. Oh, that worked. That was a positive because my goal function, my error function is I want to get that. I want to put that in my mouth, right? So I eventually learned to grab something and put it in my mouth through this reinforced learning of going of over and over again, repeating this process, getting better at it. That's what this would do, right? So you put your goal in this loop and just keep doing it. You fail a lot, right? But every time you fail, you improve those weights until you get where now I can do that. Now I can stand up. Now I can walk. Now I can run. And so that's the idea behind what this loop is. Finally, after it's been through the prescribed number of training sets of games that you want it to try, it builds a model out of that neural net, and then it passes the model back to the game to say, okay, here's the complete model you would use to play the game, to play this based on the best learning I had from playing 50,000 games. This is what I end up with, my best play for that. And then that's the part I said in a robot where I would take this model, this trained system, and put it into a flat file, move that flat file over to my robot, and have the robot read it up into its system to operate. All right, let's take a look at the play training game right here. It returns, this is where it gets big, and this is where the speed isn't such an issue on a lot of microprocessors as much as it is the memory. This thing's a memory hog. It works almost exclusively with doubles or floats. So big byte values to start with. And then it has to have a lot of them. It has to have many multi-dimensional arrays. It has to have an array of weights that show the weight between every node and the node it's connected to. You have to have each one of those for each of the layers in the network. So you've got, we've got a 9 by 18 array already of doubles, and you've got an 18 by 9 and a 9 by 3 and a 3 by 1. Right? Those are all necessary. You have to have those for the weights, for the biases, and for the values, the activation numbers, the value of the neuron itself. So you end up consuming a lot of memory, and that doesn't usually fit well in most microprocessors. Once you've trained the model, now what you really only have is the two-dimensional array of weights for each layer in the network. So you cut it way down. You cut it down by a third. And so if your inputs and outputs can be fairly small, it'll fit well as an execution inside the microprocessor. But you make okay, so play a training game, you pass in the network, and then there's two options here you can put in that says, do you want to play this AI versus AI, or do you want to play it versus a person? And so if full AI is set, then the computer just plays both sides. And this is sort of set up to do that. I think I was telling you about, talking about where the human could play the other side, but didn't implement it that way. You build a brand new game though to play the training game. You build a brand new game. You build your inputs and output lists, and then you build a new model. This is really just setting up a new copy of the game for you to work in here. And then while the results are still unknown, while there's no winner or loser or tie determined, you kind of figure out whose turn it is. You figure out the best square. This looks exactly like what we looked at in Maine when we're actually playing against a human, right? So this is still that same move, back and forth, right? So sometimes, the other thing that I am doing here that's different is there's two options, and I do part of the algorithm, part of the numbers, part of the training games are AI versus AI. So both the X and Y are trying to make intelligent moves. Then for part of the algorithm, part of the training set, I do the AI algorithm versus a random selection. And that's where this random, so in this else, this 63 and 64 line, right, I get all the valid squares, but then I just pick one at random and say, well, if this one's it, then try it, right? And that gives you a different look at the data. If you just do the AI versus AI move, you're assuming that the opponent always makes the smartest move. And by throwing in some training data that's just random, you're hopefully trying to train the AI to not be fooled by a bait and switch move, right? Where they make some stupid move that makes you make a move that then lets them come back with a better move. So that's why you kind of you train to sort of both sides, and there's a percentage of which one does each. And then you get the board that says a double, which is really converting it into the neural network model. And then you get the game results, and you just kind of this decodes if anybody's won or not, right? And then you put the progress into there, right? So turn 1, turn 2, turn 3. You want to train it. Each move in the game is going to be a different model. It has to, or a different result, right? It tries to win through that. Any questions about it so far? We'll play a couple of games and I'll show you how it works. If there are no questions. All right, so right now I've got the number of training games set to 1. So not going to train up much, going to give it one example, just basically say, hey, here's how you play tic-tac-toe. You put your X's and O's in here and you try to get in a straight line. So it doesn't really know much at all. And then it makes it bigger. So it trained itself. Obviously took about 31 milliseconds to train it, get it all set up and train it. All right, so the way you build the board is the right is the key, the left is the tic-tac-toe board. And so there's numbers from 0 to 8. X goes first, we're X in this case. So I'm going to pick 4, the middle square. So I'm going to move there. And then it put its O right below me. So like, okay, I'm going to put mine in 0, the upper left square. And it blocked me, which is pretty smart. But now I can put mine in 6, block him, and force him to lose. So now there's no way he can win, because I can put mine in either 3 or 2 and win. So I'll put mine in 2, and X wins. All right, do it again. This time the computer moves first. They've put theirs in that bottom square. That's not a very intelligent place to put their square, put their X, either in the middle because there's more ways to win, or a corner box because you can take advantage of stupid moves from the other player. But I'm going to put mine back in the middle. They put theirs upper left. So I'll put mine, lower right. Right. Now they made a move like, well, why would you go there? That does nothing. Well, because it doesn't really know how to play yet. And then I put mine at 0, take advantage of their stupid move, and I win again. All right. So 1 training set's not good. Let's go to 20 training sets, which still isn't a lot. So this time it trained in 37 milliseconds. Let's see. I go first. I'm going to go 4 in the middle again. And then go 0. Oh, nope, I'm not going to let it do that. See, it didn't block me. It just says, oh, okay, well, I'll go here. I'm going for the win. It doesn't, but it's ignoring the fact that I could win first. So that let me win again. It went there. I'm going to go in the middle. And it went lower. It went there. So I'm going to block it there on the lower right. And then it made a move to there. Again, not knowing that I'm going to win by just putting one there. All right, let's try more training data. Let's go to 200 training sets. Okay, so now it took 57 milliseconds to train. I'll go in there, middle again. It went above me. I'm going to put it on 6. Went below me. Again, not smart. I'm going to go to 2, and I win. It goes on there. I'm going to go 4 in the middle. Put it on both sides of me. I will go to 8. Goes there. And then again, not realizing I'm going to win if I put it there. Yeah, it's still kind of stupid. So let's go to 2000 training games.
Is there any way to take the game you're playing and make that part of the training?
Yes, that would be that thing I was telling about where you go inside that training loop, and every game you play, you go back and redo the model. The code would be a little more complicated, but yeah, I could certainly do that. What I saw with this was, though, the number of games it took, and part of this is just I didn't spend a lot of time on the configuration of the nodes and the way and the learning factor, the adjustment parameters for it. But the way it is right now, the number of games that it takes to actually get a good model built up is so high, you'd never get that many games played. It doesn't learn very fast, right? This specific way I had this set up, it just doesn't learn very fast. So the improvement from game to game would be slow, right? I mean, I just went from 200 to 2000, so I went up by a factor of 10. It's now about a quarter second of training time, but let's see if it plays any better. Okay, I'm going to pick the middle, kind of the same plays I had been doing. I will let me do upper left. See, it's still not making great plays, even at 2000 training sets. Let's do an 8, and I win. Now let's try this. Now, see, it did make a better move here. Now that we're getting to 2000 training sets, it realizes there are more ways to win from the middle square. If you pick an edge, if you pick one of the top center, lower center, left or right, there's only 2 ways to win from each of those spots. if you pick a corner, there's 2 ways to win, right? Or 3 ways to win: diagonally, horizontally, and vertically from any of the 4 corners. But if you pick the middle, then there's 1, 2, 3, 4 ways to win from there. So mathematically, that middle spot is a good place, right? So it's learned, and you really, after playing about 2,000 of these games, you really learn that that middle spot has a higher probability of winning. So it took its move there first. I'm going to go 0, and it put a move low, and now which I'm gonna block, right? And now it took a move again based on not on me winning, but on what's going to try to make it win more. And then I win. Whoops, sorry. 1, 2, 0, 1, 2, 2, and I win. And let's see how it does if I move first. I'm going to go ahead and pick the 4, just to be consistent with what I've done. Go to 0 next, right? And then I'm still going to be able to beat it because I can go 6. And then it makes its move to block me, and then I go to 2, and I win there. So let's bump this up again to 20,000.
I guess one thing they never talk about is those self-driving cars must weave and mess up for a long time. They only show when it's working. Look how
Right.
flawless it is.
Yep, exactly. And then when you get an error condition, like, oh, somebody unexpectedly steps out on the road, if you just have one training set for that, one training example of that happening, and you've got 10 million training sets of driving down a good road, that one training set isn't going, or that one training example isn't going to materially change the weights to all of a sudden react to that. It's going to take a lot of training data of somebody stepping out from the side of the road to get that knowledge really built into the rest of these weights, if it is at all, right? You might have, remember that one diagram I showed with 3 clusters of data on it? Maybe there's really 3 neural nets there, and you have to run all 3 of them in parallel. And if any of them show a problem, they have to react to it, right? So often, because of that problem of the data being so different, you end up with those, remember those clusters of data sets, the 3 data sets I showed? Because you end up with that very regularly in complex situations, what you end up having to do is build hybrids of these AI pieces. So you may have 5 or 10 or 15 different training models looking for different things. You might have one neural net that's just looking for people stepping out in the road, period. May have one neural net that's worried about keeping you in the road. You may have another one that's trying to identify snow, or all these things have to work. And then a higher level piece of AI that has to interpret how important those are, right? So you may be looking at the snow and like, okay, I got snow, so I'm going to adjust my driving habits based on this, but still going to keep it in the middle of the road. But then if my neural net that says somebody's stepping out, or there's a car crossing my path unexpectedly, when that fires, everything else has to stop, and that one has to get priority, right? And so trying to lump everything in, every decision into one neural net usually means you got just an idiot for a neural net. It can't figure everything out at once. They're good at classifying closed sets of data, but they don't do well when the data gets very smeared across a lot of domains. Does that make sense?
Yeah, yes, it does make sense. Thank you.
Okay. All right. So 20,000 training sets this time. Took about a little less than 2 seconds. So let's go first. Let's go back to 4 first. And then let's try 8. All right. And then, well, it still didn't find us. So we're still able to win there. Its moves are a little better, but it's still looking at how it can win and not really looking at us. Its move, it didn't make it back to the middle again. It decided to go there. And then but it's trying to win, so we're going to go 2. And then we're going to go 6. So we're still beating it at 20,000. Let's dock it up an order of magnitude again. So now we should be at 200,000. Yep. This will probably take 30 or 40 seconds to, probably 30 seconds to run. Eh, 13, 14 seconds. That's not horrible. All right, let's try it again. Take our move. So it picked that move. I'm going to pick 2. And then I'm going to pick 8. Doing better, but still not there. Still got to win it. Still got to beat it. Pick that one. I'm going to pick 4. I'm going to block it. And then see, it picked an absolutely silly move again based on that move. It should have tried to. It should have blocked me, which is 5. This is where I said it doesn't play real well. It's not good at classifying these moves. But let's go to 500,000. Whoop. This will take probably close to a minute to run. But you can see over here on the right on my diagnostics tools, the CPU is not really doing much, but it's running about 12 mega memory to run this, which isn't huge, but if it's a microprocessor, it's a lot. If it's a Raspberry Pi or a computer, it's not anything, right? So that's 34 seconds to run that. Let's see how well it does. There's a 4, so it made that move. Let's go 6. Okay, and it's going to let me win it again. But at least it blocked me one direction that time. Yeah. And then it's taking the middle square again.
Craig, a question. I mean, one of the things in training is the loss function, right? And what the loss function is. If you somehow did the loss function so that there was more loss with a lot, that the loss function penalized a loss more than it rewarded a win, would that help?
Yeah, that would help. And I've not tuned this much, but yeah, then that's where the real secret to these neural nets is in the training data and in the tuning of the parameters, the number of nodes, the loss function, or the evaluation function you're using. You know, it right now is biasing. It's winning more than against it losing. And I think you're right. I think in this case, making it better at not losing would be an improvement on it. But see here on this one, it actually made a pretty good move, right? Because now, no matter where I go, if I go over to 5, for instance, and try to work down that way, it blocks me and it has me. So at 500,000 games, it's finally playing a pretty reasonable game, and it's going to win, right? Because now I'll go block out 0, and it made a stupid move, right? It had me, and then it chose for whatever reason not to make that move, but it should have won there. So if I go on a little more and maybe do, let's go ahead and finish this game out, and end up being a tie this time. First time, I think that's the first time I think it tied me. So let's let's see if going to, I don't know, 700,000 training sets will get it. Because what we're doing every time is reinforcing the good moves and unreinforcing the bad moves. So more of them just keep adding those numbers up and up and up until you finally see a winner. But yeah, Stuart, I think you're right. I mean, absolutely, it would do that. Adjusting those numbers, tuning the parameters, that's where success is with these neural nets. And unfortunately, there's no way that I've ever heard of to be really deterministic about what the numbers should be. It's a lot of trial and error and a lot of just playing it and seeing, this isn't working. Let's go try that and see. And we change the cost function out for something that prevents a win. You'd think, okay, there's going to be more ties now. Perfect game. If you move second, the best you can do is a tie in tic-tac-toe. I'm gonna do that same basic move again, see what it does. See there and there, and then I'm gonna put 6, and then I've got it. So now that's me winning, and then let's see what. Oh, I have to go and X wins. Yep. All right, it picked the middle. I'm gonna pick an edge. It picks a 0. And then I'll pick 3. It picks that. I got to pick 6. And then I got to pick 1. So we've got, so now it fought me to a tie. Let's try, oh, I think I just killed it. I did. Let me rerun it here.
Does it throw away your previous trainings every time, or is there a way to retain that? Yes. Okay.
Yeah, I could have. I didn't have it retain the training. I could have, and it would be a good way. In a real world, you'd probably want to do that. Unless, of course, you change the training model. If you change, like Stuart suggested, if you change the, no, it wasn't Stuart. Who was that? Sorry, I'm not watching. So it wasn't whoever suggested that. If you change the algorithm, now you got to go back and retrain from scratch. But if you change anything, right? If you change the number of nodes, you change the weights, you change any of that stuff, you're going to have to retrain it. So there'll probably be limited function for most of that, most situations. Puts it there. Let's go there. It blocked me, but now I'm going to be able to go there, and it blocked me, but I can still go 8. So I can beat it still. See where it goes there. I'm going to pick in the middle. And then if I make a dumb move, let's see what it does. I'll pick 8, which then forces it which picked the right spot, and now it forced it into its win. Because now if I pick 6, it did, but see, it still isn't picking good moves for it. It really should have picked that top center spot to win. So there's still some problems with it. And I think it might be, I'm not 100% sure there's not a bug in the classification program.
Yeah, there's got to be something going on, because it should have trained enough to see that.
That should have been enough to see that. I'll look at it and see if I can find something wrong. There might be, I'm kind of suspicious of a bug there with as bad as that's getting.
I guess in my case, I was kind of talking about saving your session, and most of the stuff I've been seeing is like these the autonomous driving. In some cases it's 2 sets of lines. I'm talking about like RC car size stuff.
Mm-hmm.
So you'd almost need to have, okay, I'm going to do a 10-minute session, pause that session, but retain that knowledge, so to speak, and then, you know, maybe recharge a battery or whatever and do it again.
Yeah, in that case, saving the session would be valuable. Absolutely would. One of the things I want to do once we all get back together and meet at the science center, where we can put the thing out, is bring the line following robot out and teach it to follow the line, and just let it run and bop around the line and miss, and it'll finally learn to stay kind of on the line, and then eventually run the course. And the goal function for that would be keep the line in the middle of the robot and complete the courses in as fast a time as possible. And so those would be the two things. You train it to those two outputs. Output one would be, you'd probably have probably two outputs in that case. You'd have turn left or turn right for like or your direction. So a proportional output that goes from -1 to +1 that says should you veer left or veer right, +1 or -1 or 0 is stay in the middle. And then the other one would be the speed controller, how fast do you go between 0 and 1, just to try and get that out. And your evaluation function would be to get around the course as quick as possible. Well, it would learn when it was going too fast, it would learn that it can't control itself longitudinally, because you hit a sharp curve and it would slide, or it couldn't turn fast enough to make the curve. And then it would also learn on straightaways it can accelerate, because it doesn't move off the line so much going straight on those straightaways. So that's why my next step is with this, is to put it on a line follower and get the board out. But so it wouldn't be real instructive here, where you can just see a little bit of this off the video camera. So
a lot of the jets and stuff they're using, a couple of them look like it's a small version of a foot track, like your kids run at school, the track, but like a smaller version of that with like some sort of bend, so it's not all right or left turns. And then there's a few where they have them running hallways of what presumably is either a high school or a college. So camera, computer vision is what it is, but camera vision is what they're using. But that's kind of something I'm interested in. I don't know if I'll get there. I got to put some effort in, really.
Yeah, and that's where I keep always forget the name of the thing. Hold on, I'll find it. I got it up here.
Are you talking about a chip or program?
No, it's the program we were. TensorFlow. Yeah, I always forget that. TensorFlow has a lot. Most of what you see from TensorFlow is machine vision based, right? Those classifications. You're taking images in, and it's looking for, as it scans that image, it's looking for different objects, recognizing different objects. That's how it's doing it, just running the same neural net algorithm. But you've trained it to find those things. And so when it finds them, then it builds a box around the image and says, there it is.
And Craig, one question is, I know like some of the car examples you were mentioning, I've seen the Amazon has that AWS racer, which, and I'm reading about it a little bit. I know they do something called reinforcement learning, which I know is distinct from supervised or unsupervised learning. Are those all running on neural nets? It's just a different way of training neural nets, or?
Reinforcement learning is it's a thing about unsupervised learning, that if you start, one of the drawbacks of unsupervised learning is if you get a lot of extra noise in the system, like weird things it sees once in a while, it'll start to learn about those things and lose some of the knowledge it had from its original training set. And so what they need to do is go back periodically and replay the known good knowledge to get back to those things. Because an unsupervised learning could be just free-form car that learns new things as it sees it, right? But you can unlearn, because of the way this algorithm works, just adding up numbers, those numbers can take away from other nodes, right? It has the wrong number of input nodes or hidden nodes now to correct for that. And so they need to go back and reset that. If you're able to, the thing the human brain can do that computers can't yet is dynamically reassign the attachments of nodes. So if you need all of a sudden more input nodes or more output nodes to do something, your brain can reassign those over a period of hours to days. That's what kind of long-term memory is reassigning those connections. If we at the point where computers have hundreds of petabytes of RAM to draw from, then you've got a pool of memory that you can go back in and start to reassign these nodes dynamically at runtime. You can't do that now, right? Once you build the number of inputs, the number of outputs, you train to that, and that's what you got. You just got to go back in and re-execute. To be a truly intelligent, independent learning thing, you have to be able to resize those layers as the environment changes. And animals can do that, and computers can't yet, because they don't have a surplus. And the way you have to, if you add new nodes, for the most part, you have to go back in and retrain the whole system again. And that's not the way animals don't work that way. If we lose some nodes, we don't have to go back in and retrain. We're losing brain cells every day. From when you turn about 20, you start losing brain cells. We still seem to manage. So
one thing, so watching your Tic-Tac-Toe game, you got to see its choice. One thing you did not get to see is what the weights were for its other choices, I suppose.
Right.
So you have 9 cells. You got before it makes its move, you got 8 choices. I'm curious if it would help you see the issue if you saw that it said, "Oh, I had 3 choices that had a number, and the other ones were zeros," or whatever
Yeah, no, it could. It very well could, to print those out beforehand for a game this size. One of the things that people dig at neural nets about is, it is kind of legitimate. You can never tell why, and when it's actually running, not the training, but once you're actually have it in production and you're running it and it makes a decision, you really can't tell why it made that decision, because it's a very transient thing with inputs and outputs. If you had 200 inputs and 25 outputs and 300 nodes in the hidden layers, you just don't know that interaction, right? It made a decision. You just got to trust it, and that's hard for a lot of people to do, especially more mission critical pieces.
So I guess if a person, and they probably couldn't, but if they could draw it out on a board, the math that it's using, it would be like in the movies where Will Hunting sees this board as big as the room and he makes the answer at the end.
Yeah, you can. Yeah, it really can be, because you've got. And I think people do is, once they really start to understand how the big networks work, they start to take nodes away. Part of it's to save memory. If you see nodes that are historically just never really come into play, you can just take those out, save the memory. You can also rearrange nodes, add more nodes, force weights higher. People play a lot of games to make things work right for their specific situation. You're making it more of a savant every time you do that. And that thing about this tic-tac-toe game, what I really came to realize was, this is trying to classify board moves for something as simple as tic-tac-toe. it's much easier and quicker just to do it's called a mini-max game, a mini-max search. So you start with an empty board, and then you make all 9 possible first moves and as X, and then you evaluate each of those moves based on X. And then for each of the first 9 moves, you make the 8 more moves that O could make and evaluate it, but then change the sign to negative so it works against you. And then you can just keep doing an exhaustive search. You build the entire, every move out that could be made. And then when you're playing, whatever the first move is, the best next move to make that'll lead you to a win. And so there's not a lot of variability in it. That's a better solution for something like this, and it's this size. It's kind of a decision tree in effect that you're building up.
Can we go back into code? I'm kind of curious of what was going on there, especially with the how it was evaluating the position. Can we look at that?
Yeah, let me get that. Let me reshare. All right, let's take a look at the evaluation function here.
Now, this method, you have a full AI. Is that pretty much always set to true?
No, what happens when this gets called, that gets passed in. And to trace down to see where it is, train the model. Trainer.train. It's up here. So what happens in that loop is depending upon.
There's a third of the time it's full AI.
Yeah, a third of the time it's full AI. Yeah, and we could change those from, and this is then random, the other part. So that's what changes. That'll be every other one, and then there's sometimes that both of them are, but every lines up. But yeah, so that loop is what'll switch those things around. So the best square current is the model. So the model.best square, which is so right here. The neural net.compute is what we want to find. And that is okay. So it's passing that into board after is this double array. So get board is double is probably what we want to see. Yep. So it determines makes the array you're going to pass out. It sets your point of view to say whether, am I X or is it not X? So X point of view is 1 if you're playing as X, because you want to evaluate it. This is where you evaluate your win versus your loss. So if you're X, it's a 1. And then you go for each element in the board. If the board's a -1, then you subtract that value. And I think this is just a weak algorithm for determining that. I think that's part of the problem.
Yeah, it's not really determining win or loss. It's just.
Yeah,
to kind of determine just where the X's and O's are.
Oh wait, that's not what I wanted. Then that's not the one I wanted. Let's go back and I was wrong. Sorry, I told you the wrong spot. Model current dot best square. Oh, okay. So you have to think about how this actually is working again. So gets the valid squares. It actually asks the neural net to compute the value of that. It's the backprop that we want to look at, not here. Yeah, so the backprop is the teacher.
Yeah, I guess even in unsupervised learning, you got to have some method of saying this is a winning position. You were successful.
Right.
Lose, you just lost.
Yeah, I'm trying to figure out where that is here. Going back. I mean, I can zip this code up to you, Josh, and send it to you too. That's not a problem. Play the training game.
One thing would be kind of neat, and I mean, I don't know if you'd have time of the day to watch it all, but that one game or movie rather from a long time ago where the guy ends up talking to the army computer and says, "Hey, I want to have war," and then at the end of the movie, he has it play tic-tac-toe really fast.
Oh yeah.
To really, yeah.
Take up all the CPU power. Yeah.
War games.
Yeah. War games, right?
Yeah.
So in that situation, I guess you could say it was artificial learning, or at least a concept. And they got to. There was video in it though, where you saw it playing tic-tac-toe really fast.
Mm-hmm.
I wonder, is there a way to? Maybe it's too slow when you do that, but would it be possible to watch it play?
Yeah, it could. But if you're going to go through, we went through what 200,000 games, and if you let it stay up there for a second just for you could see it, that's 200,000 seconds that it'd take you to watch it. I don't know how many days that is, but that's a long time.
Part of my reasoning is I wonder when it's practicing, does it ever win? I guess that's kind of where I'm headed. Watching is how I would do it on the cheap, but it's probably not the most sensible way.
Yeah. We can look at this. I think this is just a really weak algorithm for calculating the best score. I think that's also, I think you're touching on probably another issue that it comes up with it, which is there's a lot more ways to lose than there is to win. And so I wonder if that biases the output set, because a lot more of its training data is you've lost anyway. So maybe it's sort of training itself to lose. So, but the evaluation function, this is where it ends up. I think the piece needs to get added though, Josh, is it doesn't check for winning and losing. It just checks to see how good is this position compare, and then adjust the weights. But it never looks at the board holistically. Never looks at the win holistically, and says, does this get me to a winning solution better? I think I need that needs to get put in here.
Yeah, I think the get results would need to be fed back into the algorithm somehow.
Yeah.
Which, yeah, I don't know how you do that, but
I have to look at it a little bit, but yeah, it was kind of beyond the scope of the presentation. So it was really to show about unsupervised learning. How you don't need to have, or you can generate those sets or get them by play or by experience instead of having to have it pre-calculated.
because in this case, I guess the score looks like, it's scoring. It's using its own scoring system, which is kind of even all the time. It's almost a random. Because if you're just saying, okay, I get a -1 if there's an O in there and a +1 if there's an X, and I think you had like a 0.01 if there's nothing or something.
Right.
That's always going to kind of wash out to even randomness. There's no bonus given for anything useful.
Well, it adds it will add it up because this for each of the board positions. So it's going to go in this loop where it gets the board as a double. It's going to say for the current cell I'm in, if it's a -1, then yeah, I think this is doing is it's not scoring. This needs to get changed because it's not scoring consecutive X's or O's. It's saying which one do I have more of on the board.
Yeah, it's scoring like as if like it was a Go game or something where you just had to have more pieces on the board.
Yeah.
If that was changed to have a little bit of evaluation, to have that basically that code from get results.
Yep.
Was,
that needs to get down in there.
So it could score 3. If you had 3 in a row, then all those would have a higher value.
Right.
And then I think that would totally clean that up.
I think that would make it a lot better. Yeah.
Yeah.
Yeah, because that's what it's using to evaluate the results, and it's not. This just isn't. This is not selective as a winning board. It just selects better boards. It selects cells. This is back to the classification part of it. It selects individual cells that statistically, when it ran its training set, led itself to wins more often or led itself to better results more often. But that doesn't mean for the game you're in, it's a good move, right? So when it was picking some of those, like it was set up to win and it picked a completely silly move, that's because that cell was better to play in its training set than the one that would have caused it to win, right? It never does look to see whether the next move can make me win. And so what you want to do is put in here somewhere, I have to look and see where, but when you're going through each cell, if that cell is going to make me win, which is this logic, the get result, if that can come back as a win, then you want to just pick that one, not even run through the network. And if it's going to cause your opponent to win, you want to pick that one too, because actually you want to pick that first. So you look for the cell, and first you need to say, is my opponent going to win off of this? And if it's true, you just pick it because you got to block him. And if it's false, then it says, well, will it make me win? And if that's true, then you pick it because you want to win. And if neither one of those are true, then you just want to go pick your statistically best move. And I think that would take care of it. You have to look to see first in the pick next here when you're doing this best square, right before you do this, any of this stuff up here, like right in this area, like line 20, right above line 20. No, sorry. Line 20, yeah, right after line 20, you would want to put a check in there to see if that one you're choosing is a win for you, a win for the opponent. And if it is, that's your square. And if it's not, then go back and pick your other one.
I think
that might be more conventional. I'm trying to think of, because if you start doing that, that's like a kind of conventional algorithm of just,
yeah,
now it knows the final move. But if you want to actually learn, then really,
well, this is back to my comment in the presentation. Is this is just not a really good algorithm to solve this problem. You know, if anything, this highlights neural nets just don't solve everything. They're classification algorithms, and so what you're classifying is, I mean, it literally this points out a bad part of neural nets is it's classifying each individual cell as overall its chances of winning or losing by picking that cell, but it doesn't see.
This is probably a brute force problem. I mean,
Yeah,
tic-tac-toe, but still, it'd be interesting to see if if it had a better evaluator,
yeah.
how
I can
well
play
it
with it.
would do versus brute
Yeah, we
force.
can play with it and see. But I said it's just not. If you were really trying to solve tic-tac-toe or any deterministic game like this, it really isn't the right one to do. There's no real variability in it to figure out. So what its training is, it just goes through and trains and says, you know, when I picked this cell before, it used to be, it statistically has been a pretty good cell when all the rest of these cells are empty or are full. So it's just not a great algorithm for solving tic-tac-toe. I don't think if the problem was to solve tic-tac-toe, I just don't think you'd pick this algorithm. But you know, it was really a shot. I think hopefully it showed the algorithm and the concept and sort of how it goes about things. And I think it really highlighted some of the limitations, which I hope it did too.
Yeah, it was an interesting presentation. Thanks.
Okay.
definitely opened up my eyes